Non voglio rubare ulteriore tempo perché è molto più importante quello che Nagendra avrà da mostrarci e da dirci in merito alla soluzione da lui realizzata, e quindi lascio la parola a Nagendra per illustrarvi l'evento e quindi il progetto che è oggetto dell'evento.
Grazie Paolo, ciao a tutti, buonasera. Adesso spiego in inglese, per favore, scusami. Ciao, thank you for Databricks User Group Italia Centrale for hosting this session today. We are going to dive deep into very practical data engineering challenge, how to reliably ingest highly volatile external data. I will be walking you through a project I built called the Italian Real-Time Environmental Digital Twin. We are going to look under the hood at how to use Databricks, the Medallion architecture, and Lakeflow declarative pipelines to build a system that doesn't just process the data but actually heals itself when things go wrong. Before we look at the architecture, just a quick introduction. My name is Nagendra, and I am a data engineer at Engineering Group here in Rome. My journey into data engineering is a bit unconventional. From 2017 to 2022, I completed my master's in nanotechnology at Sapienza University. My research required running massive complex statistical models and computational simulations. That experience taught me how to handle large data sets, and it naturally evolved into passion for data analytics and data engineering. Today, my day-to-day focus is on architecting scalable data pipelines and monitoring systems, specifically on the Databricks Lakehouse platform. I love the challenge of turning raw, chaotic data into automated, real-time business value. Here is our roadmap for next 35 minutes. We will start with the vision, what we build and why. We look at the high-level overview of the Medallion architecture. Then we get to the code. We look at the ingestion and the bronze layer, specifically how to survive the API changes. We'll move on to the silver layer, focusing on deduplication and change data capture. We will cover the gold layer where we apply our business logic. Finally, we wrap up with some engineering highlights focused on cost optimization and pipeline resilience. Let's kick off by looking at the problem we set out to solve and the final output we achieved. In the world of data engineering, environmental metrics like weather and air quality present a unique challenge. They are highly volatile. Temperature, wind speed, and pollution levels change by minute. The fundamental problem is the cost of stale data. If our pipeline runs on a daily batch schedule, the data is completely useless for real-time monitoring or alerting. You cannot use high pollution warning based on yesterday's air quality. To solve this, I designed a live digital twin, a self-healing automated pipeline built to handle the volatility of upstream APIs. The target scope of this project was to continuously track the environmental state of four major Italian hubs: Rome, Milan, Turin, and Florence. I always like to start with the end in mind. This is the final output, the real-time environmental digital twin. The dashboard updates continuously, providing a top-down view of the country. At the top, we calculate live national aggregates, averaging the temperature and the PM 2.5 and PM 10 particulate levels across our target cities. Below that, we have an interactive geographic heat map and city level granularity, breaking out wind speed, temperature, and specific air quality indexes. As a business user, this dashboard is clean and reliable. But as engineer, we know that building a simple dashboard requires highly complex, resilient backend. Let's look at the architecture that power this. This brings us to our architectural foundation. To build this, We need a platform that didn't force us to choose between flexibility and performance. We built this entirely on Databricks Lakehouse platform. On the left, we have the Delta Lake aspect. We are pulling highly unstructured raw JSON data from external APIs. The Lakehouse allows us to dump this directly into the cheap, scalable cloud object storage. In the middle, as data moves to the right, it enters Delta tables. This is the warehouse aspect. Delta brings structure, ACID transactions, and reliability to our raw data. Spanning across entire architecture uh, is the Unity Catalog Metastore. This provides a single unified governance layer. We can manage security and access control for our raw JSON file in exact same place we manage access to our final dashboard. It provides us truly single source of truth. Here is how our specific project maps to the architecture. On the left, you will see a critical design choice, decoupled ingestion. I wrote two independent Python features, one for weather, one for air quality. They run independently from a Spark processing pipeline. Why? Because external APIs go down. If Open Meteor crashes, our Spark cluster doesn't fail, it just waits. Once the data lands our Medallion data flow, first the bronze layer, unstructured raw JSON data is appended continuously to build a historic log. Next, the silver layer, where the data is filtered, deduplicated, and strongly typed. Finally, the gold layer, a materialized view that joins these streams together into business ready data optimized specifically for our dashboard. To move the data through bronze, silver, gold layers, I used Lakeflow Spark Declarative Pipelines, or SDP. If you have ever built a traditional structured streaming job in a notebook, you know the pain of imperative programming. You have to manually manage the checkpoints, directories, write complex retry logics, and manually orchestrate which task runs after another. Lakeflow Spark Declarative Pipelines changes this paradigm entirely, and it is declarative. Instead of writing code that tells Spark how to process the data step by step, I simply declare what I want the final table to look like. The framework reads my code, automatically resolves the execution order, and builds the DAG you see on the screen. It handles the incremental update and continuously tracking natively without me ever handling to maintain the manual checkpoints. This drastically reduces boilerplate code and infrastructure overhead. Now let's look at the actual code, starting with how data enters the system. This is our Python feature. It is incredibly lightweight. We use the standard request library to ping the Open Meteor app. Here we have the Open Meteor app. Notice the error handling, except response.raise for status. If the API rate limits us or returns a 500 error, the script gracefully handles it. The most important part is the payload structure. At the bottom, we don't just save the raw data. We wrap it in a metadata envelope. We attach the city name, an ingestion timestamp, and the source URL. We then dump this raw JSON string directly into the Unity catalog volumes, our landing zone. Again, this is decoupled. Spark is not waiting on the API response. The bronze layer, incremental streaming with autoloader. Once the JSON lands in the Unity catalog volume, our Lakeflow pipeline takes over. Here we define our bronze streaming table. The magic here is format autoloader, format cloud files declaration. This invokes Databricks autoloader. Autoloader is designed specifically to ingest millions of files from cloud storage incrementally. It keeps track of exactly which JSON file has already processed, ensuring we never process the same file twice. We also add a processing timestamp and extract the underlying file name from the metadata. This gives us perfect data lineage. If a stakeholder ever asks a question, a value on the dashboard, we can trace it all the way back to the exact JSON file that it's generated. The Flex, surveying the API chaos with schema rescue. I want to highlight one specific line of the code from the previous slide because it represents a massive quality of life improvement for data engineers. Option cloud files schema evolution mode rescue. Let's talk about the reality of external APIs. They change without warning. Tomorrow, the weather API might add 3 new columns or change a temperature value from an integer to a string. In a traditional pipeline, this schema drift causes a fatal error. The pipeline crashes, the data stops flowing, and the engineer gets paged at 2 a.m. By setting the evolution mode rescue, we build a safety net. If unexpected or mal-informed field arrives, data Spark doesn't crash. Instead, it isolates the unknown data into a dedicated underscore rescued underscore data column. The pipeline keeps running and the dashboard stays alive. And we ensure absolutely zero data loss. So, our raw data is safely inside the lakehouse. Now we have to clean it and manage the state in the silver layer. Guarding the gates, data quality exceptions. Because we are feeding a real-time dashboard, bad data can be allowed downstream. In Lakeflow Spark declarative pipelines, we handle this using declarative data quality exceptions. Look at the decorators at the rate DP expect or drop. We are telling the pipeline that city and ingestion timestamp must not be null. If a corrupted JSON payload makes it through, we don't want to crash the pipeline. We simply want to drop the specific bad row and continue processing the rest of the valid data. Also, notice that I defined the step DP view here, not a table. I'll explain this cost optimization benefit of that a bit later in the presentation. Inside the same view, we have to deal with heavily nested JSON. A great feature of PySpark is schema on read for complex types. We can navigate the JSON tree using a simple dot notation. You can easily extract raw weather data, current weather timestamp, temperature, and instantly aliasing it to clean, strong typed column name temperature. This step transforms the chaotic nested API payload into a clean columnar format that is ready to be joined and queried. This is arguably most critical engineering logic in the entire pipeline. Change data capture. Because our data is streaming in every 15 minutes, the bronze layer is appended only log. By the end of the day, we'll have hundreds of rows of ROM. If we plug a dashboard into that, it will break. We don't want a history log. We want digital twin, which means we need exactly one row per city representing the absolute current state. Lakeflow Spark declarative pipeline provides a native function called create auto CDC flow. We define our target table and then we establish the rules. So here we have defined the source layer and here the target layer. And here in the key section we'll tell to group it by city, sequence by ingestion timestamp. When the conflict arises, multiple rows of ROM, we'll tell you to look at the timestamp to figure out which one is the newest. Stored as SCD type 1. This means slowly changing dimension type 1. We are instructing the engine to simply overwrite the old data with the new data. The engine handles all these complex absurd logics under the hood, ensuring a silver table is perfect deduplicated snapshot. So we have clean current data for both weather and air quality. Now we want to move on to the gold layer to merge them and apply business value. In the gold layer, we finally unify our decoupled streams. We perform a inner join on the city column between our silver weather table and our silver air quality table. I chose an inner join specifically to guarantee that the final view only surfaces locations where we have complete picture, both weather and pollution data. Note the decorator here materialized view. We are instructing Databricks to pre-compute and catch this joined data. This is crucial for performance. When our dashboard refreshes, it doesn't have to execute a heavy join on the fly. The data is already materialized and waiting. The gold layer is also where we translate raw numbers into actionable business insights. First, we have a time conflict. Weather and air quality are fetched by different APIs at slightly different times. Which time is current time? We don't know. We use the f.greatest function to compare these two events and automatically select the absolute latest timestamp. Here we can see this. Second, we derive a business value. If I tell a non-technical stakeholder the PM10 level is 55, they might not know it. That's a good or bad. We use a simple when otherwise statement to flag the PM10 level over 50 as high pollution. We do this in the pipeline so it becomes a global governed truth, not just a calculation hidden in the dashboard. So, before the data reaches the final dashboard, it passes through the metric layer. This is a YAML defined schematic bridge. The metric layer handles presentation logic so our dashboard doesn't have to. For example, our entire pipeline runs in UTC, but our stakeholders are in Italy. We use this YAML file to automatically convert the timestamp to GMT plus 2. We also use this to enforce numeric formatting like decimal places. Most importantly, this layer makes our data AI ready for Gen BI by defining synonyms, telling the system that city, location, and municipality all mean the same thing. We empower users to ask natural language questions of the data, and the AI knows exactly which column to query. And that brings us to full circle back to the dashboard. Because the rigorous engineering in the bronze, silver, and gold layers, this dashboard is what we call zero logic. There are no complex filters, no massive SQL joins, and no time zone conversions happening in the visualization layer. It strictly acts as a presentation tool. This guarantees real-time reliability. The dashboard is simplified, reflecting a highly governed, self-healing, deduplicated backend architecture. To wrap up the technical portion, I want to highlight two specific engineering decisions that makes this architecture mature and production ready. The first is cost optimization. In cloud data engineering, you pay for what you store. If you remember, back to the silver layer, we were flattened the nested join JSON and applied our data quality rules. I explicitly used the DP view decorator instead of a table. If we used tables for the every intermediate transformation, we would be materializing gigabytes of redundant intermediate data to our cloud storage every single day. By using views for the intermediate praising, the data is processed entirely in memory and passed downstream. We only write to the disk when we reach the final CDC table. This result is much faster pipeline execution and significantly reducing cloud storage billing. The second highlight is indopotency and resiliency. An indopotent pipeline means that running it once has exactly same effect as running it 100 times. Because our bronze layer uses autoloader, to maintain a pristine, untouched history of every single API payload we have ever received. We can safely rebuild on the pipeline at any time. If the business decision to change the pollution threshold from 50 to 40, we can completely drop our silver and gold tables and replay the pipeline. Our CDC logic guarantees that as the historical data floods back through, it will perfectly reconstruct the single last state without ever duplicating a record. It gives data engineers total peace of mind. I want to leave you with some actionable, and I have made this entire architecture open source. If you scan the QR, it will take you directly to the GitHub repository. You can fork the project, review the Lakeflow Spark declarative pipeline code, and see how the Medallion architecture is constructed line by line. If you want to run it by yourself, don't have any enterprise account, there is a link here. It will take you to the Databricks Free Edition sign up. This provides zero cost environment designed for students and hobbyists, where you can recreate this exact pipeline. Thank you so much for your time and attention. Today, it's been my privilege to share my project with the user group. My email, LinkedIn, and GitHub are on the screen. Please feel free to reach out if you want to discuss Medallion architecture, Lakeflow Spark declarative pipelines, or data engineering in general. With that, I would love to open the floor. Does anyone have any questions about the pipelines, the CDC logic, and also how to handle the external API? So in the meanwhile, I will try to share my Databricks Free Edition window to show you how the process run in real time. So here is the pipeline that I have shown you previously. This is the job. So these are two fetcher Python files, air quality data and weather data. And here is the main pipeline. If we can open, I think it's better I share the whole screen rather than window. So this is the weather pipeline code, and I think you can see the pipeline here. Weather pipeline, yes. This is the structure of the pipeline where we have. These are the streaming bronze layer. This is the view of air quality silver source and weather silver source, weather quality. And then we are moving on to a single source of truth, the air quality silver and the weather silver, and then to the current environmental matrix, which is the gold layer. So to be more clear, I would like to show you how the data is being dumped into all these layers. So in the bronze layer, so this is the raw data, that this is the landing zone where I have created the files to land here using the API fetcher. This is the landing file. So to be clear, I will just open one file to show you the JSON JSON file, the payload. Then this data is once it comes into the landing zone, so here is the air quality. So here is the air quality. This is the source path that I have shown you previously, and we will be creating a table using these files. And the table looks something like this, the weather quality table. So sample data, just I'll select compute to show you the data. Yeah, so this is the data, like all the payload getting ingested into the bronze layer, like for each city at the given timestamp, the raw payload data, the JSON script, the source from where the data is imported, the file name, and the processing timestamp. After this, we'll move to the silver layer. In the silver layer, we have the view where we extract the data from the JSON file. So here is the extraction where we are using the accept, drop, the expect or drop values here, the exceptions. This is the extracting the files from the JSON file. After this, we are creating the silver layer where we don't have too many records to a single city. We have only one record, which is the latest record. This is because we are using create auto CDC flow. So here we will be creating we will be using the source table, the view, and we are storing the data in the target table as air quality silver. So here we are using the key to group by city and sequence by ingestion timestamp, and as SCD type 1 where we delete the override the data. So to show you the silver table, uh, so the finally we have in the silver layer only four major cities of Italy, and also only the latest timestamp with the event time and the required values, both in air quality table and also silver table, sorry, weather table. So now after this, we will be joining these two tables in the gold layer using a materialized view. So this is the table, and here are the joins. And finally, okay, just a minute. And finally, the table turns out to be like this. So this is the final table comprising of the temperature, weather data, the air quality data, and also other required parameters for the business layer. So after this, we will be the jobs and pipelines. According to the flow, we'll end up with a dashboard generation. So this is our dashboard. So this was the last date when we have generated the environmental matrix. So this is the dashboard that we have been that you have seen in the presentation. So I will show you the back end of the data. So here we have created a metric layer using the YAML file. So these are the dimensions that we are using, and also these have been given a comment, the format type, and the time, the format, and etc. So this is because it would be easier for Gen AI to read these comments and the expressions and directly answer your questions without any problem. So this is the backend metric layer. If you can see, there is also UI representation, so where you can see how you have modified the data from the raw gold layer to a specific dashboard view. So here I have extracted the city, last update timestamp, the temperature, wind speed, weather code, PM10, You can see the data types here too, the air quality and remaining other required columns to the dashboard. So if you can see the dashboard, this is how the dashboard looks like. So also, to be more interactive, I would like to run this pipeline right here right now, so that you also have the idea how does this work and everything. So I'm just triggering the run now. So in the meanwhile, I'm open to any questions if anybody is interested. So you can clearly see how does this work. So the fetch air quality and fetch weather data are running. So now we can see the two have succeeded. So now the pipeline launches.
Prendo un attimo la parola perché abbiamo Daniel che faceva una domanda riguardo alla sicurezza sul bronze layer per mantenere l'idempotenza all'interno dei dati caricati. La spiego io adesso in italiano, poi semmai dopo daremo una risposta più approfondita. Comunque il Databricks nel caricare i dati, come in questo caso ha fatto vedere Nagendra tramite i file, automaticamente tiene traccia dei file già caricati. Quindi anche se il processo viene arrestato e riattivato, tiene traccia di ciò che è stato già processato, quindi non lo riprocessa. E il fatto stesso che, come ha spiegato Nagendra, viene utilizzata la modalità SCDP di tipo 1, quindi il CDC viene automaticamente versionato per il timestamp che viene indicato in fase di caricamento e quindi è garantito che il dato ultimo mostrato è l'ultimo valido nel flusso di streaming dei dati che vengono letti. Tenete conto che l'SDP è un near real time o volendo real time mode per caricare i dati e quindi avere un flusso continuo di dati che aggiungono. Quindi il timestamp viene utilizzato proprio come chiave per fare in modo che automaticamente le procedure Databricks prendano sempre l'ultimo dato valido. Prego, Nagendra.
Ecco, il dashboard è aggiornato. In questo job c'è anche opzione per notificare, scusami, spiego in inglese. These pipelines also have an opportunity to give you notifications like these jobs. In the task section, you can see if I open this dashboard, you can see, so every time this pipeline runs, I get a mail stating that I'll get a snapshot of the dashboard that it's been updated. So I haven't added any triggers, but we can add trigger according to your like the file arrival, or in this case it's better to be scheduled because it's an environmental metrics. So we need update every, let's say every minute, or every minute, let's say 15 minutes, every 15 minutes the dashboards get updated. So this gives us a real-time experience of how temperature varies time to time. So if we can see the dashboard here, so the latest update is today at 7 p.m. The national mean temperature is 32 degrees. The national mean PM2 value is 10.45. National average PM10 is 13.7. And you can add more cities. We need to change the Python fetcher file. So we can add more cities, and also it will be the Spark declarative pipelines will handle any amount of data with ease, and very easily it can handle this data and create the table as it is as we require. So we can see the temperature in the Firenze, Milano, and etc. here. And sorry, I haven't shown you the fetcher files. It would be really helpful if you see the fetcher file. So I have mentioned the locations here from where the data must be extracted. So these are the locations: Roma, Milano, Firenze, Torino. So this pipeline runs a loop, fetches the data, and stores the payload in the landing zone, which is here: the volumes, weather, raw data file, air quality. And same goes with the weather quality. And here, from here we are extracting the JSON files. It's open Meteor website where it's free for everyone to access this and get the link here and extract the JSON files and create your own pipeline according to your interest. And thank you, Paulo, for giving me this opportunity to share my project with this Databricks User Group Italia. And if anybody have any questions, please go ahead and ask. I will try to answer your questions.
Ok, allora vediamo di fare, faccio un piccolo recap alla questione. Oltre all'aspetto puramente tecnico della soluzione mostrata da Nagendra, che utilizza le nuove funzionalità che Databricks già da diverso tempo, già da qualche anno ha messo in campo, cioè il Lakeflow e l'SDP, cioè lo Spark Declarative Pipeline, per poter processare i dati in una maniera dichiarativa, cioè non scrivendo proprio codice relativo alla fase di gestione dei dati, ma appunto descrivendo entità che muovono dati in modo dichiarativo. All'interno di questa dichiarazione di movimento dei dati possiamo inserire il controllo di qualità e determinate soluzioni che semplificano la gestione in senso lato del movimento dei dati e otteniamo dei benefici a livello operazionale, ma soprattutto otteniamo benefici laddove, dovendo movimentare dati con una certa velocità e con un timing ben definito, tutto questo lavora con i Databricks in modalità serverless, quindi con attivazioni che vengono create puntualmente nel momento in cui servono e subito dopo decadono. Quindi è anche ottimizzato il consumo delle risorse e naturalmente i costi che ne derivano. Quello che è interessante però della soluzione, cioè la cosa che mi aveva colpito anche quando Nagendra me l'aveva sottoposta, è proprio il principio che sta dietro a questa soluzione. Nagendra l'ha applicato a una cosa che oggi è tra l'altro molto sentita, quella della qualità dell'ambiente, della qualità dell'aria, la valutazione delle precipitazioni, ma la stessa identica soluzione la possiamo applicare a qualsiasi tipologia di dato dobbiamo ingestionare su grande scala. Volessimo fare una soluzione per l'acquisizione del traffico cittadino piuttosto che dell'andamento dei consumi energetici in ambito comunale, provinciale o regionale, piuttosto che di altre soluzioni in cui, come mi è capitato di farlo a me personalmente nel campo dell'automotive, raccogliere i dati delle centraline degli autoveicoli per processarli e valutarli in tempo reale. Ecco, questa è la soluzione che è facilmente riapplicabile, cioè non abbiamo uno schema rigido, ma soprattutto quello che è importante notare e che piace a me far notare è che Databricks è una piattaforma a tutto tondo, cioè non devo mettermi lì a studiare architetture di cosa mettere in campo. Oggi Databricks copre l'intero contesto che va dai database transazionali, integrando e avendo anche dato modo durante l'ultimo summit di vedere proprio l'ulteriore passo svolto nell'integrazione di un database transazionale interno modalità serverless altamente scalabile e performante con quello che è un data lake, quindi il mondo analitico. Databricks su questa è probabilmente la prima che è partita e sta creando proprio una piattaforma sulla quale io opero a prescindere dal dato, mantengo un'unica copia di dato che posso gestire sia in modalità analitica, quindi creare dashboard, creare tutto ciò che serve al mondo IA, ma altresì posso creare tutto ciò che serve a un mondo front-end di presentazione verso utente, tant'è che nei prossimi eventi andremo a puntualizzare, a vedere come creare applicazioni front-end gestite all'interno del Databricks in modalità serverless, quindi altamente scalabili e fruibili da parte degli utilizzatori esterni, e come queste applicazioni possano rispondere in tempi estremamente rapidi grazie proprio alla presenza del database transazionale che è sincronizzato con i dati che acquisiamo e movimentiamo in modo massivo con la piattaforma analitica. Quindi questo primo spunto che abbiamo voluto dare con questa breve presentazione di questa applicazione vuole essere il seme per dimostrare le grandi capacità che oggi offre Databricks e che stanno continuamente in potenziamento, perché ogni settimana ne tirano fuori sempre nuove feature, soprattutto legate, ripeto, a quello che è la connessione del mondo transazionale con il mondo analitico, e tutto governato tramite appunto lo unit catalog che fa da grande controllore a tutto ciò che avviene all'interno, quindi una rendicontazione completa di chi, cosa, come, quando e perché accede a questi dati, ma soprattutto il fatto che poi tutto questo viene contornato ormai dall'omnipresente sistema di gestione agentico che ormai pervade all'interno della piattaforma intelligenza di Databricks. Io chiudo, siamo stati perfettamente nei tempi come stabilito. Chiudo ringraziandovi della partecipazione e dicendo che naturalmente potete scrivere a Nagendra o contattare sui vari canali o chiedere direttamente sui vari social informazioni se vi dovessero servire. Ringrazio chi è partecipato per la prima volta a questa sessione, spero che l'abbia trovata interessante, forse poco comprensibile non conoscendo specificatamente il mondo Databricks. La cosa che, ripeto, non voleva essere né troppo tecnica, entrare troppo nei particolari, proprio per dare spazio a una visione che può essere invece proprio di business, quello che non abbiamo visto oggi ma che vedremo prossimamente, proprio anche magari con l'aiuto di Nagendra e tutto, è come questi dati che entrano, al di là che sono dati di tempo, di qualità dell'aria o delle precipitazioni atmosferiche, come questi dati possono essere maneggiati e fruiti in modo estremamente semplice proprio grazie alla presenza degli agenti da parte di persone che di tecnico non sanno nulla e tutto quello che vogliono è poter fare domande al sistema in modo semplice per ottenere risposte ai loro bisogni. Quindi una governance fatta all'interno dei dati che permette poi di poterli interrogare in modo naturale e ottenere risposte altrettanto in modo fruibile da parte dei vari operatori. Ok? Perfetto. Io vi ringrazio di nuovo della partecipazione e vi invito a rimanere agganciati ai canali social dove appunto daremo visione dei nuovi eventi, dei prossimi eventi, molto più in questo caso spostati sull'ambito appunto IA e utilizzo della piattaforma per quello che è la gestione dell'intelligenza artificiale e il supporto agli utilizzatori di questo tipo. Ringrazio a tutti nuovamente, buona serata e grazie di aver partecipato.
Grazie a tutti, buona serata.
We bring our errors, wins, and dreams and turn them into living streams. So ask it loud, ask it clear, there is always someone here. From your first step to your breakthrough day, the community lights the way. One question can light the spark, one answer can guide the heart, one learner can rise and lead, one helper can plant a seed. We learn, we share, we build, we grow through every challenge, row by row. Databricks community, we stand as one. The journey starts, but it never ends alone. Visitors come with curious eyes, looking for a path, looking for a sign. Learners come with no